Thank you and good morning. I always like being first up because at least for 20 minutes I'm the best talk of the day. Of course it will be the best talk of the day anyway, right? Okay, tough crowd. Anyway, I'm going to talk about the Tangerine SDR, which came to being when Nathaniel from HamSCI asked if we could help him pick an SDR for the Personal Space Weather Station. And after doing a bunch of research, we determined that no, we really couldn't, because there wasn't anything that would do the job within the budget that we had. So we decided we're going to roll our own. So what is the project? The key things are modular, and I can't do a pointer, I guess, but modular and open source. Like, does this work? Modular open source hardware and software platform. So that's the key thing to remember throughout this whole talk. And I'm going to go kind of fast, but these will be up online, so you'll be able to peruse them at a slower rate if you so desire. But it's all run by a group of volunteers and students and professors, and like Nathaniel said, so it's a collaborative effort. And we'd like to acknowledge the two sponsors here, NSF. Most of this work is done under NSF grant at the beginning, and then we've got a couple of generous grants from ARDC to help us flesh out the number of prototypes and to help us out of the big hole that the supply chain has got us all into. So, what is it? What is it? And I'm going to focus on the use cases of space science, since that's what we're all about here. But it's supposed to be a wide range of cost-based performance, and the idea is make it modular so you can pick the features that best suit your use case. And it's all open source, hardware and software, and hopefully it advances the state of the radio art. And there's lots of target applications. We're going to talk about the Personal Space Weather Station today because that's the main one for today, obviously. And it's also the first use case. But we do have a few other amateur features, and the idea is that if you're going to spend money on a personal space weather station to help the science community out, or what you're interested in, you could also, if you're a ham, you could use it for ham radio applications. It's configurable with an easy-to-use web interface. I don't know how many of you people have tried to set up SDRs before and gotten mired down in a whole bunch of computer stuff that's really hard to deal with. It should be relatively easy with a web interface. We're going to integrate WhisperNet and reverse beacon network and some FT8 features. And since it's a direct sampling radio, you're going to be able to do all this at the same time that you collect data for the Personal Space Weather Station for ionospheric monitoring. Whoops. Yeah. So getting down, I'm going to dive deeper and deeper as we go here. So it's an Ethernet-based direct sampling receiver with an Fpga doing the heavy lifting on the digital end. Full coverage from 100 kilohertz to 60 megahertz. Now that means not scanned, not tuned, but we sample the entire band at the same time. Web-based configuration, like I mentioned, and multiple UDP streams. So the idea is you sample the entire 60 megahertz spectrum, but you can pick out multiple narrowband streams out of that 60 megahertz and send them out as UDP streams simultaneously. So you can listen to 160 meters and 6 meters at the same time using the same analog to digital converters in the front end. And while we're focusing on receive capability, transmit capability is in the future because we plan for it. Okay, so what are the components of the Tangerine? The data engine is the main component, which is kind of like the motherboard of your PC. It holds 1 or 2 RF modules which plug onto it. Also, it holds a clock module which also plugs onto it. And we'll get into what these modules do or have onboard hardware in a minute. Also have a low-speed, we call it a low-speed expansion adapter fixture. And I have to look at this because, of course, you have to have cool acronyms if you're going to do computers, right? Like Raspberry Pi Hat or Shields or whatever else. So we have the Leaf, and it's an enhanced Raspberry Pi Hat is what it is. And I'll get into what it is actually in a minute. And then one of the kind of unique features of the Tangerine is that we marry it up with a single board computer, but we do it over Ethernet. Over gigabit Ethernet. So therefore, if you don't like the performance that you're getting out of your single board computer or you need more horsepower, hook it up to your i9 desktop if you want. It's just Ethernet, so it can connect up to any computer that you have that has the power that you need to do the things that the PC does. We split the task between the FPGA and the PC, but the PC does a lot of heavy lifting, so you may need a more powerful one than a single board computer. And then we've got some optional sensor modules that plug on either to the Raspberry Pi or the single board computer or directly onto the data engine. So here's a block diagram. It kind of shows the data engine assembly on the left and the single board computer on the right. And I'm going to talk a little bit about these and just very quickly run through the different components. So this is the FPGA and the local memory and the resources that the FPGA needs to operate. So we're going to use an Altera Max 10 M50, if we can ever get any. That was supposed to be a joke, but it's not really very funny. Anyway, memories for the FPGA, some memory for data buffering, like for Ethernet, some for multiple FPGA images so you can reconfigure very quickly without having to download a new image. It'd be an onboard image, basically. And then micro SD card for updates, kind of like a Raspberry Pi, where you can plug in a new image with an SD card. And a single wide input power supply, your station supply will run this. Communications, we have 5 gig USB 3. There's single lane input and output, full duplex, 5 gig USB 3 channel. And there's a USB 2 channel, and some people ask me, well, why'd you put that on there if you got USB 3? Well, the answer is because the chip only costs $4, and it will give you an opportunity to take your DVB dongle, the little $20 SDRs that you can buy everywhere, and you can plug it on here, and you can do some amazing things with processing that you couldn't do with a Raspberry Pi, because now you have an FPGA in line with the data. We have dual gigabit Ethernet ports, so that you don't have to have a switch externally, so you can plug it into, and if I can go back here, I can show it here. You have the single board computer on the right, but then you notice in the, on the lower left, the data engine connects directly to the network. So now you don't need a switch, an external switch. You connect one port to your local network, one port to your single board computer, and you're on the air, so to speak. This is a picture of the data engine. The big part there in the lower center is the FPGA. We have all the parts ready to go to build this, but we can't get the FPGA, so we're chomping at the bit to do that, but I'll have a solution for that in a second, a temporary solution. Okay, the RF modules now, there's 2 of these, 2 sockets for them on the data engine. And they're 140-pin MEC connectors, very high-density connectors, high-speed connectors. We started out with M.2 connectors, which are 75-pin, until we tried to connect up all the features that we wanted. Then we realized 75 pins was not near enough, so we ended up with the 140-pin connectors. And the current board that we have, and actually, this is the first board that we actually have, is this the camera? This is a panel of 5 RF module boards that I just got the day before I left for the HamSCI conference here. And they're in process now. We'll have actual boards out the end of the month, March 31st. Anyway, it's a dual channel, 14-bit ADC. We're clocking it at 122 megasamples per second. Also has an onboard amplifier and attenuators and a noise source, so we can switch in a calibrated noise source. I could switch it in and out. And the other thing it has is an optional user-defined plug-in filter. That's my favorite one. So if you live right next door to WABC in New York, and they're 50,000 watts and they're taking you out, you can put a notch filter in or a high-pass filter in and plug it on the board and eliminate the interference. This is the block diagram of the module. It's a little bit of an eye chart, but you can see on the signals come in on the right, flow to the left, through the attenuators, the optional filter, the low-pass filter, the amplifier, and the ADC, and then out to the 140-pin connector to the data engine. And that's a picture of these. I didn't know I was going to have a real board to show you guys. Next, the clock module. So you might ask, well, why a clock module? Well, you really want to be able to timestamp this data very accurately. So you need a GPS disciplined oscillator, which is what this clock module is. It plugs right on the data engine, gives you an ultra-stable TCXO disciplined by several different kinds of GPSs, and we have 3 of them that actually we can mount on the board, and you can pick the performance level you want and the price you're going to pay. If you want more performance, you're going to have to pay more, but not everybody needs that, so we didn't want to lock you into a $200 GPS when a $25 one will do. And the high-performance one is actually a dual-band GPS, so it allows you to do some electron content measurements in the ionosphere that the single-band ones don't let you do. We spent a lot of time improving the performance of this, making it as robust as we can. And notice at the bottom in red, what we're planning to do is create a small little carrier board that you can buy the clock module and plug it onto this carrier board, and you'll have a lab-grade GPS-DO for your shack or for your workshop at a better price than you can get anything that will perform as well as this does. And here's the 3 variants, high, medium, and low. There's the block diagram. It also has 9 outputs, but we're only going to use about 4 of them. But again, those will be usable for the additional board, the carrier board. And there's the layout. And what you can't see is the GPS is on the right-hand side. On the back side is the other 2 GPSs, and you populate one or the other. So we get 1 PC board layout, and we get 3 different levels of product. The leaf module. Okay, so a leaf module is an RPI hat, which is what's in blue there, and then we extend it down and we put a high-speed connector on the bottom, so it gives you more options for what you can put on the RPI hat, or the leaf board, because you've got some high-speed I/O. Most of the I/O on the Raspberry Pi is I2C and low-speed interfaces. We've got some differential pair high-speed interfaces on the bottom there in orange. And this is meant for general I/O expansion like PTTs and keyer paddle and things like that if you want to build a radio, or GPIO for whatever you need. And I'm going to move on a little bit, change it a little bit. This is a sensor module, which is a magnetometer, and I've got an example of a production version up here also. And this will plug onto a Raspberry Pi as a hat, or it will plug onto the data engine on the leaf connector. And what it does is it measures the magnetic field of the Earth on 3 axes. And this is up to Rev E now, so we've got it pretty well debugged, and we're ready for production. Again, I have a part shortage, but that should be solved in May. So you should see these being sold by Tapper pretty soon. By Hamvention, I'm hoping. This is how it all plugs together. And you can see that in the black is the data engine. The left-hand side is the green, the clock module, the leaf module, the upper right. And the RF modules are in blue, and they're underneath. They plug on the back. So it creates like a 3-board stack. And I'm just going to skip this for now. That's a comparison of other SDRs for your amusement. So this is what it's going to look like. I think Nathaniel might have shown a slide like this, but this is what you would use. The dual ADC receiver board, a magnetometer plugged on, most likely to the client computer, GPS-DO on the data engine. And then connect it to the internet so you can store data on the internet on the cloud as you acquire it. So what else can you do besides personal space weather station? Whisper monitor, FT8 monitor, and remember, it's simultaneous reception of all bands, so you're not limited to tuning your radio to one frequency and just listening to that. One of the neat features that is built in the test software is looking at FT8 streams for a particular call sign, and then when it's discovered, sending you an email. So if you want to look for your buddy online, you just put his call sign in, and when you hear him, he says, "Oh, Bob's on 30 meters. Here's the frequency." So you get an email notifying you that he's on the air. And when we get a transmitter, full digital mode. So the build schedule, at the end of the month, we'll have dual channel receivers and the GPS-DO. They're both in production and in build right now for prototypes. The data engine, you notice my schedule there, that's about accurate. And the Raspberry Pi, or the magnetometer hat is dependent upon one part be in May sometime. And I'm going to skip through this because of time, but you can look at this online. There's 9 references to chips in this picture. See if you can figure them all out. And just in case you don't have time, there's the key. But I won't focus on that much. So the contingency plan, so what we're going to do, since we can't get max 10 parts for the data engine, what we're going to do is we're going to build an interposer that will go between the boards that I just described, the RF module and the clock module, and an off-the-shelf FPGA development board. So this is how it's going to play together. On the left is an off-the-shelf max 10 development kit, which we have about a dozen of, so we have them in our hands, so they can't take them away from us without violence. And then on the right is the standard, is the adapter board with the clock module and the RF modules under an RF module, only one underneath. Okay, time's up here. So this is the stack up. Way to look from the end. And thanks again, ARDC, for your grant. And I'll give a plug for Tapper. You'll hear that later on. I'm sure Nathaniel will help out with that. And one more thing. Come to us in Charlotte. See us in Charlotte in September for the Tapper DCC. It's more of a engineering-oriented version of this, which is a science-oriented version. And I'm going the wrong way. That's it. Thank you very much.
Thank you, Scotty, for that nice talk. We do have a few minutes for questions if anybody has questions in the audience. Okay. I'm going to bring you the microphone so people on Zoom can hear too.
Let's see, you haven't said much about sensors or preamplifiers. Are you amenable with like pretty much any sensor that a amateur would have, or what's the, do you have recommended ones?
Okay, this works. Yeah, we haven't really done a lot of work on sensors yet, but we're offering multiple I2C ports on the Raspberry Pi header, which will be also implemented on the data engine. So any of those, and the idea is you'll be able to use off-the-shelf sensor boards that talk I2C and just plug them on, and then you'll have to write some software. And the idea is to provide the I2C ports availability over the Ethernet so that it's just software you have to write and not FPGA code. But other than the magnetometer, that's the first one we have.
If you are in a situation where you can't run an Ethernet cable to your set, is there a way of doing Wi-Fi, or will that screw up all your measurements on that board if you need to get Wi-Fi onto there to get your data out?
The problem with Wi-Fi is just not fast enough, because you really need pretty much all of the gigabit Ethernet bandwidth to get your data out. We do have a USB 3 port, which is usable. We haven't really intended to support that out of the gate, but it's available there, and it's actually faster than the Gig E, but you may have the same problem connecting a USB cable, that if you can't connect Ethernet, you may not be able to connect USB either. So I guess you can't really use Wi-Fi as the answer.
Scotty, thank you for the shout out for ARDC. And I want to tell everybody here and online to go to ardc.net to check out what he's talking about. And you have forgotten to tell us what your new position is.
Oh, yeah, well, I don't like to brag. September, I was elected president of Tapper. So, thank you, Bob.
All right, I think that's all the questions, right?